Hey guys, today we're going to talk about the water cycle. As you can see here, I've got a landscape drawn and I've got a water. And you'll notice that the water line stops and becomes like a dotted line. And of course, what that is actually water below the surface of the earth. The water cycle does revolve around liquid water, at least for our senses. However, there's a lot more to it. And this groundwater is permeating the soil. And it's not exactly like underground river. What it's much more like is maybe like a cereal with a bunch of milk in it. And in between each one of the particles of the cereal is the milk. So the cereal is completely saturated with milk. The milk fills each particle of cereal, fills all the space in between it. That's much more like what this groundwater is. The dirt that is there has water in all of the spots where air normally would be. You'll notice the black line below. That line is an impermeable type of rock or soil. It could be clay if it's going to be impermeable there, but that impermeable layer is very important to holding groundwater in place. And the groundwater itself is an aquifer. It is what we would draw things out of the well. But if we're talking about the water cycle, the first thing we have to talk about is evaporation. We have that sun up there, the sun is shining, it shines on the water, it adds heat to the water, and water will leave its liquid form and turn into a gaseous form. It doesn't have to boil to do this. There's actually a pressure, if there's low enough humidity in the air, for water to want to get into the air. Those water particles turn into water vapor, and that's the process of evaporation. After water is evaporated and goes into the atmosphere, eventually it will condense. And so I'll draw a cloud up here to represent condensation, or water that has changed form from a gaseous state into a liquid state again. But water doesn't condense just on its own. It won't condense in the air unless it's got something to condense on. And we call that a condensation nuclei. And a condensation nuclei can be something as simple as dust. It could be something a little bit more complex, like a large volatile organic compound. But more often than not, we're talking about dust that water condenses on. It's a similar thing to what happens inside a car. If you're in a car when it's raining out and there's a bunch of people in there, the windows are rolled up, all of the windows fog up. And that's because water will condense on the window. Of course, there is an optimal limit for how much water the air can hold before it eventually has to fall. It gains mass as it continues to get bigger and bigger droplets, and eventually it falls to the earth. This is a process called precipitation. And of course, there's a lot of different types of precipitation. You can have rain, sleet, snow, hail, all different kinds of forms. But in general, you have the cloud have too much water to hold, and it then rains on the earth. Once it hits the ground, it will become runoff. It will run into lakes, streams, and some of it will even go through the ground into our groundwater source and help recharge our aquifer. The space it passes through before it gets to the groundwater is called a recharge zone. Now, I've drawn some rain and some stuff on here, but I'm going to go ahead and erase it because I want to add some different stuff. The first thing that I really do need to draw is a plant, and I'm going to choose to draw a tree. I draw this tree and it represents all plants. I just use a tree simply because it'll simplify my drawing. And this tree, of course, uses groundwater. It will pull it up from the ground using its roots, and it will use some of that water, but a large amount of it will actually be pulled right out of the tree and up into the atmosphere through the open pores called stomata. Each time a tree has an open stomata, it loses water. Some plants, like succulents, or what we call cam plants, like cacti, will actually close their stomata during the day to help save this water. They're trying to stop a process called transpiration. That's where water leaves the actual leaves of a plant and is pulled up into the atmosphere. Transpiration is very similar to evaporation, with the caveat that it happens in a plant. Next, we have to talk about some human interactions. And so I'm going to go ahead and draw a house here. I'm going to start by drawing a little porch, try to put a little rail on it, and then I'll finish up by drawing maybe a little bit more stereotypical what you might think of a house. I draw this house to represent all humans. It's representing our human interactions in taking water up and using water in every way that we do use water. So if a factory uses water, this house represents all human activity. Again, I do that to simplify this. One key thing that we as humans do, especially in this area of central Indiana, is we draw our water from these underground aquifers, from groundwater. We pump it up through wells. A well is very simply a hole in the ground that goes to that saturated part of the soil. Early on, to dig wells, you would just have a group of individuals who would dig a hole until it was waist deep or shoulder deep in water. You stone that well in, and then you drop a bucket in it. Our wells today are a little bit more sophisticated. They'll use pumps, and they'll pump that water up. And we use water in a variety of ways. We use it to bathe, we use it in cooking, we use it for drinking, we use it in washing our clothes, we use it for watering our gardens or fields, we use it in factories. We use a lot of water in our daily lives, especially if you're an American, because water is easily and readily available. If you turn on the faucet, the water will come out. But when we use that water, it's put into the environment. Again, if you're watering your garden, some of it might go back down into the ground and recharge, but a vast majority of it's going to end up being evaporated back into the atmosphere. We use a lot of water, and that water plays a big role in the water cycle. And the problem is that we like to use fresh water. Fresh water is one of the lower percentages of water that's available on the earth. Salt water is way more abundant. And so because we're using fresh water, we end up taxing the system, and sometimes we have groundwater sources that end up drying up. I'm going to go ahead and draw precipitation back in to finish the cycle. And I want to highlight some key things that you're going to need for when you describe this for me on a test. First and foremost, you really do have to talk about the big three: evaporation, condensation, and precipitation. This is simple 8th grade science. They're the three major parts of the water cycle that you talk about. I'd like you to add transpiration to that, the effect of runoff, and groundwater. And of course, because we're in environmental science, you definitely need to talk about the human aspect. Us pumping the water out of the ground through wells or taking it from surface water and then putting it back into the environment. These key things are important to describing the water cycle. Now we're going to talk about the carbon cycle. And to talk about the carbon cycle, instead of starting with the ground and starting with an aquifer, we're going to start with the atmosphere, specifically atmospheric CO2. Our atmosphere is made up vastly by diatomic nitrogen and diatomic oxygen. 99% of our atmosphere are those two diatomic elements. However, in that 1%, carbon dioxide is prevalent. This atmospheric carbon dioxide is important to the carbon cycle because it's a source of carbon dioxide for plants. So let me go ahead and draw my ground here and add in my tree. Again, this tree represents all plants. So I've got my little woods here, and of course trees will pull carbon dioxide out of the atmosphere using a process called photosynthesis. They use a really awesome enzyme called ribulose bisphosphate, or RuBP, to do this. It literally grabs a hold of the carbon dioxide molecule, pulls it into the cell, and allows it to be used in the fixation of carbon. It's going to turn it into a glucose molecule, which is pretty amazing. That's the process of photosynthesis. And it's what takes atmospheric carbon dioxide and puts it in the living world. Now I'm going to draw an animal, and I'm going to do my best to draw a wolf or a dog, but quite frankly my skills at drawing are not that great, so it's probably not going to look very good. It represents all consumers, not necessarily one dog. But the idea is that consumers will eat plants, and that when they eat the plants, they will pull in some carbon that plant fixed. And so in this way, consumers interact directly with the carbon cycle. This consumer will eat the plants, it takes in the carbon, and thus kinds of seals it up. But that's not the end of it. Organisms like dogs or humans or any other carnivore will use that energy. They use it through a process called cellular respiration. And when you're using oxygen with it, it involves glycolysis, the citric acid cycle, and the electron transport chain. All of those will go together to produce ATP, carbon dioxide as a waste, and water. Of course, organisms will breathe out that carbon dioxide. However, consumers or animals are not the only ones that go through cellular respiration. So I've got to connect this line to the plants because plants themselves will use some of that glucose that they made. Next up, I'm going to draw fossil fuels. And fossil fuels play an important role in this cycle because dead plant and animal matter over millions of years will become fossil fuels. It's a stored up reservoir of carbon dioxide. And that reservoir can be accessed to release the carbon that's there. Now, it is very important that you understand that animals and plants only become fossil fuels over millions of years. They're not happening in a short amount of time. That's why we consider fossil fuels a non-renewable resource, because they're not going to renew in our lifetime. I'm going to go ahead and draw a house again, because that house will represent all human activity. And as you know, humans use fossil fuels. We'll mine them out of the ground, or we'll pump them out of the ground if it's crude oil, and we will use those to facilitate our energy needs. There really isn't much else besides fossil fuels for a high dense energy material. So I'll draw an arrow from the fossil fuels to the house, representing the mining of all these fossil fuels. And of course, when we burn those fossil fuels, we release it back into the atmosphere. We're releasing millions of years worth of stored carbon dioxide back into the atmosphere when we use fossil fuels. There are, however, some natural sources of atmospheric carbon dioxide. Some examples of that would be like a forest fire or a volcanic eruption. Both of those things will release carbon dioxide into the atmosphere naturally. These natural emissions do play a role in carbon dioxide in the atmosphere, but realize that natural emissions don't happen on the scale of what we can do with fossil fuels. I'm then going to draw in some water, and this water represents the ocean. Because, believe it or not, the ocean itself is a carbon sink, or a reservoir for this carbon dioxide. It's actually involved in a carbon dioxide exchange with the atmosphere. The more carbon dioxide there is in the atmosphere, the more that will be turned into solution inside the ocean. And there's a give and take. If there's too much in the ocean compared to what's in the atmosphere, some will be re-released out. So it's an exchange of carbon dioxide from the atmosphere to large bodies of water like the ocean. Some key characteristics to talk about when you're describing this to me on the test would definitely be atmospheric carbon dioxide, the exchange between the atmosphere and the ocean, cellular respiration and photosynthesis, and the use of fossil fuels by humans. If you get those 5 things, you will have the thorough description of the carbon cycle for the scope of this course.